morning. Today I want to continue our discussion in Chapter 20 and talk about the connection between cell potential and free energy and the equilibrium constant. Now, one thing we mentioned earlier was that these electrochemical reactions that are occurring in the voltaic cells, right, are spontaneous, right? And they have a positive cell potential, right? So what does this tell us? Well, this tells us that having a positive cell potential is an indicator of a spontaneous reaction, right? It goes along with the fact that these are spontaneous electrochemical cells. Now, in Chapter 19, we determined that free energy change, right, is the determinant, right, of a spontaneous process, that a spontaneous process will have a negative change in free energy, right? So that was our indicator, or not even indicator, but our the way that we determined whether a reaction was spontaneous. And so if having a negative free energy change determines the spontaneity of a reaction, and spontaneous electrochemical reactions have a positive cell potential, then it makes sense that there would be a connection between them, right? An equation that would allow them to be connected. Now, to sort of further look at these values that tell us about the spontaneity, right? In Chapter 19, we looked at the connection between the equilibrium constant, right, and a spontaneous reaction, right? And we correlated, or we talked about spontaneous reactions will have equilibrium constants greater than 1, or in other words, very product-favored equilibrium constants. And we developed an equation to do that, right? We said that the free energy under standard state conditions, right, is equal to negative RT ln of K, right? So there's a connection between having an equilibrium constant greater than 1, right, is going to result in having a negative delta G. And so we have these three values that tell us about the spontaneity of a process, right? We have delta G, which determines the spontaneity, and we have cell potential and equilibrium constant, which the value of these can tell us about the spontaneity of a process. So, indeed, there is a equational connection between the free energy and the cell potential, and we can list it right here, right? So the delta G, in this case we're talking about standard state, right? The delta G under standard state is equal to negative NFE at standard conditions, right? So the standard cell potential. Now in this equation, N is the moles of electrons transferred in the balanced equation, right? So if we look back at balancing electrochemical equations, we saw that a certain number of electrons move during the oxidation and reduction, right? Whether it's 2 or 3 or 4 or whatever. But N would be, in the balanced equation, how many electrons are being transferred. F is a constant known as Faraday's constant, and it relates the charge in a mole of electron. So 96,485 coulombs. Remember, coulombs is a unit of charge per mole of electron. So 96,485 coulombs per mole of an electron. Now, so we have our equation. Now, how can we connect this equation in the bigger sense, right? So we have a way to relate free energy and cell potential. Now, what about equilibrium constant? Well, if we take a look the equation from the last chapter that relates free energy to equilibrium constant under standard conditions, right? We have delta G equals negative RTLN of K. If we combine that with the equation that we just came up with, that delta G equals negative NF E cell, we can set those equal to each other because they're both equal to delta G. And with a little rearranging, we can isolate cell potential, and we end up with the equation that the cell potential at standard state equals RT divided by NF times the natural log of the equilibrium constant. Now, this form of the equation is fine. We can use this equation. Typically, when you see this equation displayed, though, they will have made some changes to it. First of all, we will typically substitute in the values of R and F, right? So R being 8.314 joules per mole Kelvin, F being Faraday's constant. We'll typically display this equation already simplified for 25 degrees. So typically we would have already plugged in the 298.15 for temperature. Now, in the standard version of this equation, we shift from a natural log to a base 10 log. And so if we plug those values in, we end up with the following equation, which relates standard cell potential to the equilibrium constant, and that is 0.0592. This is a constant value, right, which we get from plugging in that R, F, and T values and switching to the base 10 log, divided by N, again, the moles of electrons in the balanced equation, times the base 10 log of the equilibrium constant. And so now we have our connection between the equilibrium constant and the standard cell potential. And if we think about numbers, right, that if we have a K value greater than 1, that's going to end up giving us a positive value for the cell potential. So we have to have these indicators in line that if a process has a positive cell potential, it should have an equilibrium constant greater than 1 and vice versa, right? And also, of course, should have a negative change in free energy. Okay, so now let's do a couple of example problems utilizing these relationships. So the first problem here is it says we want to use standard electrode potentials to calculate delta G for this reaction, right? So I2 reacts with bromide ions to give iodine ions and bromine. So if we want to use the connection between cell potentials, right, and free energy, right, well, of course, our appropriate equation here is going to be delta G, standard state, negative N F E cell. Now, of course, before we can do this, we have to come up with the cell potential, right? So we have to come up with this. And so we're going to use standard electrode potentials to do that. So we're going to go to our table of reduction potentials and we're going to look up our cell potentials. So if we quickly look at this, right, what we want to notice is if we go through and figure out what's being oxidized, what's being reduced, right, what we see is if we assign oxidation states, right, that I2 is a 0, being an element, Br minus is -1, I minus -1, and Br2 0 with the element. So we can see that I2 or iodine is being oxidized. Right? It's going from 0 to -1. is being reduced, going from 0 to -1. And Br minus is undergoing oxidation, right? Going from Br minus to Br, losing that electron to go from -1 to 0. So we have our oxidation and our reduction. So if we look up in the table, okay, we go to our two half cells here are going to be 2Br minus aqueous goes to Br2 liquid plus 2 electrons. So that's my oxidation reaction. It has a reduction potential. Right, if I look in the table, 1.09 volts. So these are the reduction potentials. And if I write my reduction, my cathode reaction, right? I have I2 plus 2 electrons goes to 2I minus, and it has a reduction potential of 0.54 volts. So you see here that our electrons cancel out, right? If we add these back together, of course, it would give us the equation that we have above. Now, if I calculate my cell potential, so remember cell potential here is going to be cathode minus anode. Or reduction minus oxidation. So my reduction, right, is here, right, the iodine. So that's at the cathode. So I have 0.54 volts minus 1.09 volts. And that equals equals negative 0.55 volts. So we have our cell potential. So now if we go over here, and we can calculate delta G. Well, first of all, if we look at the reaction, we see that we have 2 moles of electrons, right? So we have, in this reaction, we have an N value that's going to equal 2. So we have negative 2, and of course Faraday's constant, 96,000. 485 coulombs per mole of electron. And then our cell potential, 0.55 negative. Now remember, this is voltage, and voltage is equal to joules over coulombs. And I put it this way just so we can sort of see the units cancel a little bit easier. So our coulombs will cancel, and so we're going to end up, and moles of electrons cancel here and here. This is 2 moles of electrons, and so we end up with joules as our final unit. So if we carry out the math here, we end up with a positive 1.1 times 10 to the 5th joules as our delta G. Now, we have a positive delta G, so this indicates, of course, a non-spontaneous process. And so under standard conditions, this reaction would not occur in a spontaneous way. Right? Iodine would not be reduced in the presence of bromide ions. In fact, the opposite would occur spontaneously, and you would have iodine ions undergoing oxidation in the presence of bromine, and in the presence of bromine, where the bromine would undergo the reduction. So the opposite reaction would actually occur. Okay. So this is an example of the connection between the cell potential and the free energy. Right? And we could have sort of predicted this in the very beginning over here, because we saw that we had a negative cell potential, right? A negative cell potential would have told us that this process is not spontaneous. So it shouldn't be surprising that we came up with a positive change in free energy. All right, let's do a second example here, this time looking at the connection between cell potential and the equilibrium constant. So in this example, we're going to use standard cell potentials to calculate the K value, the equilibrium constant, for the oxidation of copper in the presence of H plus ions, again, at 25 degrees. So the problem tells us that we're going to be calculating K from a cell potential. So the appropriate equation here, right, is the one that relates standard cell potential, so E cell, to the equilibrium constant. And so remember that equals 0.0592 volts divided by N times the log of K. Now, of course, before we can do any of this, right, we have to have a cell potential. Now, in order to have a cell potential, we need to calculate it from our standard reduction potentials. So again, if we look at our process here, we see that copper here is being oxidized from copper to copper plus 2, and hydrogen is being reduced from H plus to elemental hydrogen, going from positive 1 to 0. So we have our oxidation and our reduction. So if we're going to write out our cell potential, we'll write out the oxidation of the copper here. So we have copper. Oops. Copper goes to copper 2 plus 2 electrons. And that has a potential of 0.34 volts. And we have our reduction, right, which is 2H plus 2 electrons goes to H2 gas. And we have a cell potential here of 0, right? This is remember, the standard hydrogen electrode, right? The basis of our table, right? So it has a reduction potential of 0. So our E cell, so remember, so this is the oxidation, this is the reduction, or this is the anode, this is the cathode. So remember, this equals E cath minus E an. And so cathode is 0 minus 0.34. So we end up with an E cell of negative 0.034 volts. Okay. So we've calculated our cell potential. Now, as we discussed last time, right, we can have an indication here based on the negative cell potential that we're looking at a non-spontaneous process, and so we can anticipate that we might get a K value less than 1, right, indicating a reactant-favored process. But let's look at the outcome here. So if I plug in my negative 0.34 volts equals 0.0592 volts divided by N. Okay, so if we look here, what does N equal? Well, again, we have a 2-electron process, 2 electrons lost, 2 electrons gained, so N equals 2. So we got 2 moles of electrons, log of K. So if we take care of a little math here, we do a little rearranging, we can get the log of K by itself. So we have negative 0.34 volts times 2 moles of electrons divided by 0.0592 volts equals log of K. So if we rationalize all of that, we end up with log of K equals negative 11.486. Now if we think about units here, my volts cancel. And so we just get the 11.486 equals log of K. Now remember, to get K here, we take the inverse, or 10 to the, so 10 to the negative 11.486 will give me K. And so if I do that, I get 3.3 times 10 to the minus 12 equals K. And again, not surprising, we have a K value that is much less than 1, which would both indicate non-spontaneous, or in this case, since it's not a delta G, we can simply say that it's a very reactant-favored process. So we've seen some of these basic connections between our three sort of measures of spontaneity: our free energy, our cell potential, and our equilibrium constant. Okay, so now we're going to turn our attention to sort of our next step as we've been going through stuff. And so we've looked at, all of these connections under, quote, standard conditions, right? But as we saw in the last chapter, right, most real-world conditions are not standard. So we need to look at what happens under non-standard conditions. And so if we think back to chapter 19, we established this equation, right, for the calculation of the free energy change under non-standard conditions. And so now if we do a little transformation and we plug in our E cell value as free energy, so remembering that we just determined that delta G equals negative Fe. So we can plug that in for both under non-standard, right? It's still going to equal negative NFE, the cell potential at those conditions, equals negative NFE standard, and plus RT ln of Q. So that gives us this equation now, where we have the cell potential at non-standard conditions equals the standard cell potential minus RT over NF ln of Q. Now, we've obviously done a little cleanup here. We've divided through by negative NF to get rid of the NF here, get rid of it here, and now we have division by negative NF. And so our positive sign is turned negative, and we end up with the equation that we see here. Now, similar to what we saw with the standard condition equation, the way that this is commonly presented is by substituting in for RT and F, right? R and F as constants, T at 298.15 degrees. So we're going to simplify this for that temperature, and changing again our natural log to a base 10 log is sort of the standard way that we write this equation, and we end up with our final equation here of the cell potential equals standard cell potential over 0.00592 volts divided by, again the number of moles of electrons in the balanced equation times our base 10 log of Q. This is what is commonly known as the Nernst equation. So this is a fairly well-known electrochemical equation that allows us to calculate the cell potential under non-standard conditions. Now, of course, Q here, right, as we saw last chapter, is useful in plugging in whatever our non-equilibrium conditions are. So whatever the concentrations given for a particular environment, we can plug those in, calculate Q using the format for Q, and then now in this case we can get the corresponding cell potential. So if we think about the big picture of sort of what this means or what values are going to mean, so if I end up with a Q less than 1, right? So what this means is that we have a greater concentration of reactants versus products, right? So we have a Q less than 1, and this drives the reaction to the right. So if I have a Q less than 1, meaning I have more reactants than I do products, then I'm going to end up with a cell potential that is greater than the standard. So there's going to be more of an initiative to go toward the products because I have a higher concentration of reactants here. If I have a Q greater than 1, meaning I have more products than reactants, then the reaction is going to be disfavored under these conditions, right? And we're going to end up with a cell potential that is lower than under standard conditions, right? In other words, the reaction is going to be less favored or more reactant favored under these conditions. And of course, if we happen to be at equilibrium, then there is no cell potential, right? Just like we saw in the last chapter, delta G at equilibrium is 0 because the reaction is not spontaneous in either direction. So it makes sense the cell potential equilibrium would be 0 since the reaction doesn't spontaneously move in either direction. So if we look at a sample equation to look at this, and we look at our old zinc copper cell. So if we remember the balanced equation here, right? So we got two half reactions, but if we just write out the overall equation, remember it's zinc solid plus copper 2 plus ions are going to form solid copper plus zinc 2 plus ions, right? So this is my overall equation with, in this case, a 2 electron transfer. So we saw under standard conditions, we generate a cell potential here of 1.1 volts. Right? So we calculate, we look up our cell potentials for zinc, and for the oxidation of zinc, the reduction of copper, we plug in our reduction potentials, we calculate 1.1 volts. Under standard conditions, right? Remember, that's 1 molar concentrations. But if we look here, and we set it up so that we have more what would be reactant, right? So in this case, the copper ions are our reactant. Right? They are reacting to form copper metal, and we have a lower concentration of our, what would be our product, our zinc ions here. And remember that Q, right, our reaction quotient, equals products over reactants. Right? Then if my products is less than my reactant concentration, then my resultant value is this is going to be much less than 1, right? If I have a small number on top, big number on bottom. And so, as we've done it before, having a more reactant than product, right? So if we shift back here, I mean, a greater concentration of reactants versus products, and therefore Q much less than 1, drives the reaction to the right, right? So we want to make product, and so we end up with a higher cell potential than we do under standard conditions. So our goal here, right, is, to try to get rid of this copper, make zinc, right, or drive the reaction to the right. So we see that we get an elevated cell potential. The reaction is now, quote, more spontaneous by setting it up this way. Now, without showing another example, we should remember that if we set this up exactly the opposite, so if we set this up with a high concentration of zinc ions, or in other words, a high concentration of product, and a low concentration of copper, in this case a low concentration of reactant, then that means our product over reactant would be just flipped, and we'd have a much greater concentration, and we'd have a value of Q much less than 1, right? And we're going to be reactant favored. In other words, we're going to try to make the copper and get rid of the zinc, right? Try to get back to this equal concentrations, if you will, right? But we're going to have the reaction is going to be driven in reverse, or we would end up with a potential less than the standard potential. So this is this idea of if we operate under non-standard conditions, we can sort of estimate what's going to go on here. Oops. Now, we can actually take advantage of this in a way to make what we call concentration cells. And this is where our anode and our cathode are exactly the same. So we're going to set up both sides of our voltaic cell as identical. Now, of course, under standard conditions, we would get no voltage, right? Since we're not doing anything, right? But we can get a spontaneous reaction to occur just simply by altering the concentrations, as we've seen here, of one side versus the other, even if they are exactly the same. So we can use the Nernst equation and we can think about which direction that spontaneity is going to occur, right? And that's going to tell me if I can make a spontaneous reaction, right? If I'm going to get a spontaneous reaction by changing the concentration of one versus the other. Now, in general speaking, electrons, as we saw, will always flow from the less concentrated electrode, the solution, to the one that is more concentrated, right? As we saw in what we were just looking at, we flew, in that case, electrons flowed from where we had the lower concentration, right? That functioned as the anode, to where we had it as the cathode, right? And so if our cathode was more concentrated, we saw more voltage. Right? If our anode would be more concentrated, we would see a less voltage than standard state. So if this is the case, we're going to see oxidation of the less concentrated electrode, and we're going to see reduction of the electrode in the more concentrated solution. So again, if we look at an example here, again, setting up with the same side under standard conditions, equal voltage, right, or equal concentrations, nothing happens, right? We get no voltage. But by simply altering these voltages and making, in this case, the cathode side higher than the anode side, and so remember, electrons are going to flow from low concentration to high concentration, right? And so the net effect here, right, is if we want oxidation at the low concentration, because what is that doing, right? That oxidation will produce copper ions. So that'll serve to increase the concentration of the copper ions, right? And so we're going to serve to increase the concentration of the solution that is low in concentration. And then we're going to see reduction at the higher concentration. So we're going to see reduction at the higher concentration solution. And what is that going to do? That's going to use copper 2 plus, right? So the copper 2 plus is going to be converted to copper metal, and therefore it's going to lower the concentration of copper 2 plus, reducing this higher concentration. So we see the low concentration, the low side raising the concentration. We see the high side lowering its concentration. And again, this goes back to that whole idea of spontaneous mixing and these things. They're moving in the direction to try to bring these concentrations to be the same, right? So they're moving in that direction, right? So the one that is the lower concentration will react in such a way to raise it. The one that is the higher concentration will react in such a way to lower it. So this determines where we see oxidation and reduction. Okay, so now let's look at a problem under non-standard conditions. So the problem we're given here asks us to determine the cell potential, or the E cell, for the following cell using the following half reaction. So we have an oxidation process of copper being oxidized to copper 2 plus 2 electrons. Now, the thing to note is often times when they give us these kinds of non-standard conditions, they will list the concentrations with the ion. So they'll tell us that the copper ion is aqueous, and they'll give us the concentration. So they're telling us that the concentration here of copper, right, equals 0.010 molar. And our reduction reaction here involves the reduction of manganese from the permanganate ion, right, which is aqueous with a concentration of 2 molar, plus hydrogen ions, which is a concentration of 1 molar, right, so that's under standard conditions, plus 3 electrons, goes to manganese oxide, plus water. So they've told us that the MnO4, right, is 2 molar, and the H plus is 1 molar. So clearly here we're at non-standard conditions. So we're going to use our non-standard equation, right, which is our Nernst equation. And so remember that is E cell equals E standard cell minus 0.0592 volts for N log of Q. Now, a couple things that we have to think. So, in order to solve this problem, of course, we have to get our cell potential, right? So we don't know what the cell potential is. So we're going to have to calculate that. We have to figure out what N is, right? And of course, we have to calculate Q. Well, let's look at these sort of one at a time. And so the first thing is we've got to calculate the standard potential. So we have to look up what these are when we look them up in the table. So if I look up the reduction of copper, right, and so these are reduction potentials, my E0 equals 0.34 volts, and oops, let's give myself a little more room here. E cell, or E reduction equals 1.68 volts. So that means my E cell standard equals my cathode, right, my reduction, 1.68 volts, minus my anode, 0.34 volts, which gives me a value of 1.34 volts for E cell. Standard conditions. So we have 1. So now, if we look at N, right? So what's N going to equal? Well, if we look at N, we look at a 2 electron loss here. But notice we have a 3 electron gain. So of course, we can't have a loss of 2 and a gain of 3, right? We have to have the same number of electrons gained and lost. So if we were going through to balance these equations, right? If we wanted to go through and find the balanced equation, one of the things we would have had to do, right, is to take these Taft reactions and get them to the same number. So in this case, 6, right, is the lowest common number here that we can get both 2 and 3 to turn into. So we can multiply this by 3, this one by 2, and that will give me 6 electrons being lost, 6 electrons being gained, right? So we got an N of 6. So now we have to calculate Q. So Q, of course, is products over reactants. So how do I know what the product is and what the reactant is? Well, right, so my products, right, are what's being made, so that's going to be copper ions, and my reactants are what's being used, so in this case the permanganate and the hydrogen ions. So, but how can we do this so far? Well, turns out we can't jump ahead to here until we actually come up with the balanced equation, right? Because we have to know the coefficients. So let's add these together. So I'm going to do a little shortcut here. I'm not going to write everything out, but this is based on an example in the book, so if you need to go back and follow a little bit more. So I'm going to add up all the reactants. So I have 3 coppers. I have 2 permanganate, 8, and I'm writing this a little bit more brief without all the phases here, just to kind of give us what the equation is going to be. And on the product side, I'm going to have 3 copper ions and 2 MnO2 plus 4 waters. So the only thing that's really matters in the sense of Q, of course, though, is our things that are aqueous, right? Our permanganate, our hydrogen ions, and our copper ions. So Q is the concentration of products. So it's going to be our concentration of copper raised to the 3rd power over our reactants, permanganate, raised to the 2nd power, H plus raised to the 8th power. So if we plug this in, the copper equals 0.010 cubed over 2 squared, 1.0 to the 8th power. Now, so if we go through and solve all that, we get what Q is. Now, we can solve it here, or we can just plug it in. I'm going to go ahead and solve it here, right? So if we go through and do this, we got 0.01 cubed equals 1 times 10 to the minus 6th. Of course, 2 squared equals 4. And 1 times 8, of course, equals 8. So this all equals 3.1 times 10 to the negative -8. Okay, so now we're in a position to now go back here and solve. Oh, whoops. Sorry about that. I not doing my math correctly here. Let me catch myself here. Of course, 1 to the 8th power equals 1, not 8. And so that means if I redo the math quickly here, we get 2.5 times 10 to the minus 7. That's better. Okay. So now we can continue on. And we can go back and get E cell. It's going to E cell standard, right? 1.34 volts minus 0.0592 volts over 6. There's the log. 2.5 times 10 to the minus 7. So that gives me my equation. So if I simplify this, I get 1.34 volts minus, if I do all of this out, I get a minus 0.065 volts. And so if I do the math, of course, 1.34 minus a minus will give me 1.41 volts equals my non-standard. And so what we see here is our non-standard voltage is higher than our standard voltage, and this makes sense because the concentration of our reactants, right, is higher than the concentration of our products. So that means the reaction is going to want to be driven toward the products. So that's going to give us more spontaneous, which would be indicated by a higher voltage. Right. So this is how we can go about solving problems under non-standard conditions. So the key is we need to utilize those non-standard conditions to calculate Q, come up with, make sure that we've taken into account the balanced equation to get the right number of electrons, and calculate the standard potential from our standard reduction potentials to plug in here. All right, so that concludes our discussion on sort of looking at the connection between spontaneity and free energy and the equilibrium constant and cell potential, and how this works under non-standard conditions using the Nernst equation. Next time we'll look at applications of this, electrochemistry, and talk about things like batteries, electrolysis, and corrosion.